In this lecture, we are going to learn about what is known as AVL trees. Okay, so AVL tree is a very famous binary tree, and in fact it is a binary search tree. Okay, so it is a binary search tree, but it has something more than that. Okay, and that property is that balanced condition. Okay, so it is a binary search tree that is balanced also. Okay, which means the heights of the subtrees are balanced, and it ensures that the depth of the tree is log of n, where n is the number of nodes in your tree. Okay, so binary search tree, we know what is the property that okay, you have nodes. So for a parent node, everything on the left subtree will be less than equal to this. Okay, and on the right you have everything greater than, let's say, greater than the parent. Okay, and the equality can also hold. So this should apply on all the nodes, for all the nodes. Okay, so this is binary search tree. So for example, if we see, so this 7 is here, 10. So this is an example of binary search tree. Okay, so we have 7 as the parent, then on the left subtree we have left child 3 is there for the root, right child is 10. So on the right it is greater than its parent, left it is less than the parent. For 3, node 3 also, its right child is greater than parent, left child is less than parent. For 5, left child is less than 5, right child is greater than 5. So this is the case for binary search tree. Okay, where for each node, okay, so every element in the left subtree of it is smaller than it, and every element on the right subtree is greater than that. Okay, and this holds true for every node of binary search tree. But what might happen in a binary search tree is that, let's say I give you numbers insertion of 1, 3, 5, 7, 9, 15, 20. Okay, so first we will insert 1. Next what happens, 3 comes, 3 is greater than 1, so it becomes the right child. Now why we want to insert 5, so 5, we compare 5 with 1, it is greater, it goes to the right. 5 is compared with 3, 5 is greater than 3, 5 comes here, so 5 is inserted here. Then 7, so 7 is now inserted here. Similarly 9 is inserted here, 15 and 20. Okay, so this is a binary search tree, but in fact this is a linked list also, because you are just traversing in a simply in a line. Okay, so this is a tree, but a very trivial tree. Okay, where its height is really, so it's level 1, 2, 3, 4, 5, 6, 7. Okay, so it is equal to the number of nodes, its height. So this is the problem with binary search tree, that its height is not balanced. Okay, so we would like something like 7, 9. Okay, so 7, 15, 20, 9. Then we could have here, so 3, then 1, then 5. So this is much beautiful tree. Okay, it is balanced, it is binary search tree, but it is balanced. Okay, so it's not just growing in one direction, it is complete tree. It is okay, so it has very few, the height is less. Okay, so we want something like this, an AVL tree, a binary search tree with balanced condition. So this property is ensured by AVL tree. Okay, so what happens is that we want that the height of the left subtree, okay, this one, and height of the right subtree should be equal. Okay, then again, if a smart person will give me one more example. Okay, so he will say that okay, 10, 11, 12, 13, 14, 9, 8, 7, 6. So again he says that okay, I have given you one example where the root and its left and right subtree are balanced, but in fact this is also not a very balanced condition. So what we need to do, that at each node its left and right subtrees should be balanced. And how we ensure this? So in AVL tree is a binary search tree where for every node in the tree, the height of the left subtree and the right subtree, they at most differ by 1. Okay, so height of the left subtree and height of the right subtree for any node in that AVL tree will differ by at most 1. So if we see this example, so what happens now, each of the node will have one attribute which is known as height, the balance factor. Okay, so that balance factor tells, okay, so this is the balance factor, it tells the height difference between height of the left subtree minus height of the right subtree. Okay, so for this, the height of the left subtree, so 3 minus 2, so it is plus 1 here. Then for 9, this node 1 and 0, 1 minus 0 plus 1. For 8, 0 minus 0, so it's 0. For this node 2, so it's 1 height here and 2 here, so 1 minus 2, so minus 1. So we see that, and 0 for this, 1 and 3. So it has, for every node, the balance factor is 0 plus 1 or minus 1. So balance factor is, so mod of balance factor should be less than equal to 1. Then it is an AVL tree, and of course it should follow the binary search tree property. So this is an AVL tree, and of course it is a binary search tree. This is a binary search tree, but it is not an AVL tree. So if you see the root, so it's 1 2 3 here, and here it's only 1, so 3 minus 1, it's plus 2. So here this is not a binary, an AVL tree. Okay, so root is not balanced. So what we do now, so now let's look height information. So it's kept for each node. Okay, the balance factor. Now the minimum number of nodes denoted by SH in an AVL tree of height h. So okay, so we want to find the minimum number of nodes denoted by S of h. So h is the height of the AVL tree. Okay, so height is 0, then your S of 0 is 1, height is 0. Okay, so then you just have the root, and S of 0 is 1. So minimum number of nodes in an AVL tree. S of 1, height is 1, so you will have at least, so S of 1, so in this case it will be something, this is an AVL tree or this AVL tree is there. Okay, so minimum number of nodes, when will we get? Okay, so we will get that when, let's say here it is left subtree, so left subtree, right subtree. Now what happens is that, let's say the height, total height of this tree is h. This means if I remove this root node, this will be of height h minus 1 maximum. Okay, because one node I have taken, this can be also maximum h minus 1. But what we want is that we should have minimum number of nodes. So because in AVL tree you can have a balance factor which is equal to 1. Okay, so these can differ by 1. So I will want that, okay, if this is h minus 1, I can have this as h minus 2, or if this is h minus 1, I can have this as h minus 2, such that overall the tree height is h, but we have minimum number of nodes. So if we have h minus 1 here in the left, in the right subtree, h minus 2 will be on the left. Okay, so this way sh is s of h minus 1 plus s of h minus 2. Okay, so left subtree height of h minus 1, right subtree will be height of h minus 2, or either you can have right subtree of h minus 1 height and left subtree of h minus 2 and plus 1 for the root. Okay, so this is the equation, and it's very similar to the Fibonacci series. And the height of an AVL tree with n nodes, if you see, because it is balanced, so it is O of log n, where n is the number of nodes. Okay, so this is the basic about AVL tree, what is an AVL tree, and how we find out what if a binary search tree is having the AVL tree property, and how to find the minimum number of nodes in an AVL tree with height h. Okay, so this was the introduction to AVL tree. In our next lecture, so we will study about insertion. Okay, so we will see how we insert items into the AVL tree. Okay, and in that we will see that the insertion is similar to the BST, but it can cause the balance factor can become greater than 1. So how we will balance the tree again? So we will see about rotations. Okay, so we will look at rotations. So we have single rotation and double rotation. So these are very interesting things. This you will see in the next lecture, in the following lecture. Thanks a lot.